Alright, in this video I'm going to go through review 2 for our third quarterly coming up. There'll be another video for review 3 as well. Number 1, in the diagram below, points E and D are midpoints of sides AC and BC. Segments AD and BD intersect at point F. If AB is 28, AD is 30, and BE is 24, which of the following is the perimeter of DEF? So remember, the perimeter, I need all three side lengths of that triangle for. So let's just break this up piece by piece. I'm going to start with that AD of 30. The key word they give me there is that E and D are midpoints, which means AD and BE are medians because they go from a vertex to a midpoint. And the property of medians when they intersect is that they segment each other into a 2-to-1 ratio. So if I think about AD, that 30 length, if I want to break 30 into a 2-to-1 ratio, remember that's 3 pieces altogether. So each of those pieces should be 10 in length. So my smaller part FD is going to be 10, and my larger part AF is going to be 20, so that it still sums to 30. And then if I compare 20 to 10, that's the same thing as a 2-to-1 ratio if I reduce it. I can make a similar argument for BE as well. If that whole length is 24, if I want to break that into a 2-to-1 ratio, each of those pieces should be 8 in length. So FE should be 8, that's the smaller part. Double that, 2 groups of 8 should be 16. Now, in order to find the perimeter of FED there, I'm still missing that side length DE. So I'm going to compare that to AB. Because these triangles are similar, all the sides should be in that same 2-to-1 ratio. So if AB is bigger than ED, I could just take half of the larger side to find the length of ED, to ensure that that's still a 2-to-1 ratio. 28 to 14 is still 2-to-1. And when I add up those side lengths, 10 plus 8 plus 14, I find the perimeter is 32. For number 2, in the diagram below, triangle AED is similar to triangle ACB. So remember, if two triangles are similar, there's 2 properties we know. We know that the angles are congruent, and we know that the sides are in proportion. So just based off of what they're asking here, it looks like we're talking about proportional sides. Which of the following statements is true? Well, let's go through each of these and check for consistency. Number 1 says AC, a side of a small triangle, over AE, a side of a big triangle. So this is saying small over big is equal to, but then on the other side of the proportion starts with a big side over a small side. So that's not a consistent proportion. There's no way a smaller value divided by a bigger value can be the same as a bigger value divided by a smaller value. When I get to answer choice 2, it's taking a small side AB, comparing it to a big side AD, and taking a small side BC, comparing that to a big side DE. So that's the consistent proportion there. Small over big equals small over big. Alternatively, if I had a big side over a small side, I could also set that equal to a big side over a small side, but I know that works as well. For number 3, using the information given below, which set of triangles cannot be proven similar? Remember, there's 3 ways to prove triangles similar. We can either justify that they have 2 pairs of congruent angles, that all the sides are proportional, or that 2 sides are proportional and the angle included between them are congruent. So for number 1, if I'm looking, I know they have at least one angle is congruent because I've got a right angle there. But let me check the proportions. Is it the case that when I compare 12 to 4, that's the same as 9 to 3? Well, if I cross multiply there to check that proportion, 3 times 12 is 36, and 4 times 9 is also 36. So those would be similar by side angle side. Number 2 would also be similar because I have 2 pairs of congruent angles marked, so that's angle angle. But the problem with number 3 is the placement of the angle. So number 1, the sides aren't in proportion. If I check, 16 over 2 and compare that to 32 over 8, I could already see that 16 over 2 is 8, and that's 4. So there's no way that proportion is going to be true. And also the angle is not included between the sides that I know are proportional. So that's going to cause an issue for me. So that would be like a side-side angle scenario where that would not be enough information. For number 4, though, this would be a good side angle side justification for why these triangles are both congruent and similar. Number 4. If the line containing the points -2, 10 and 7, 4 is dilated by a factor of 2, then the slope of the new line would be which of the following? So here's what you need to think about. I'm just going to sketch a picture here. When I think about dilations, I normally think about stretching or shrinking, but the problem with a line is that it's of infinite length. So what ends up happening is that if I dilate a line from the origin, I'm either pushing it further away from the origin or moving it closer to the origin. So there's some things that change and some things that stay the same. You should notice that the y-intercept is going to change. I'm just going to multiply the y-intercept by whatever my scale factor is. However, notice that these lines are still parallel because dilations preserve parallelism. So if I want to find the slope of my new line, it should be the slope as the old line that contains those 2 points. So all I'm going to do is plug into the slope formula to find the slope between these 2 points. Remember, that's just y2 minus y1 over x2 minus x1. So if I label my points here as x1, y1, and x2, y2, y2 is 4 minus 10 over 7 minus -2. Now I would never write it as minus -2. Remember, 2 negatives make it positive. In the numerator I get -6. In the denominator I get 9. That's not one of my choices. But if I reduce this fraction by dividing the top and the bottom by 3, I find the slope is the same as -2 over 3. And because I need that to be the same as the slope of my image, my slope of my new and my old line are going to be -2/3. Number 5. An 8-foot wire is attached to the tree and to a stake on the ground. So here's an 8-foot wire right here. From the stake in the ground, the angle of elevation of the connection of the tree is 33 degrees. An angle of elevation, remember, is how far you go up from the horizontal. So that is just 33 degrees right in there. Find to the nearest foot the height of the tree at the connection point. So this looks like it's going to be a right triangle trigonometry problem or a SOHCAHTOA problem. So the first thing I'm always going to do is write down SOHCAHTOA, and then I'm going to label the sides I have from the angle that I know, that 33. So from that 33, that x is going to be my opposite side, and that 8 feet represents my hypotenuse since it's across from the right angle there. So you got to think to yourself, I'm looking for the opposite, and I know the hypotenuse. So I need a ratio that relates the opposite to the hypotenuse. Well, the tangent has the adjacent. I don't know anything about the adjacent. And cosine has the adjacent. I don't know anything about the adjacent. So this has to be a sine problem. So I'm going to take sine of 33 degrees, so it's always the angle that goes next to the trig function, is equal to my opposite side, x, over my hypotenuse, 8. Now, like any good proportion, I could put this over 1 and just cross multiply. 1 times x is x. 8 times sine of 33 is just 8 times sine of 33. Right, so you don't round early for these. You know, when you type this into your calculator, you should get something about 4.357, but it tells me to round to the nearest foot. So the nearest foot would just be 4 feet there. That's if I'm solving for the side length. It's a proportion I cross multiply after I pick a trig function. For something like number 6, it's going to be a little bit different. A ladder leans against a brick wall. So let's say I've got some brick wall standing up straight here. There's a ladder that leans against it, and there's a distance on the ground there. The foot of the ladder, which is right there, is 2 feet from the wall. So that bottom part is 2 feet. This picture is not going to be drawn to scale, but that's okay. The ladder reaches a height of 35 feet on the wall. So that's not telling me the length of the ladder. That's telling me how far up the wall the ladder hits. So I'm going to label this side as 35 feet. Find to the nearest degree the angle the ladder makes with the wall. So I've highlighted the ladder and the wall there. The angle included between them is going to be that angle on the top right there. I'll label that as x. So again, I know I'm going to use trig here. It's going to be a little bit different since I'm solving for an angle and not a side length this time. But I'm still going to write down SOHCAHTOA, and I'm going to label my sides from the angle I care about. So from that x, that 2 would be one of my opposite side, and that 35 would be my adjacent. I know it's not my hypotenuse because my right angle is right there. My hypotenuse is always across from my right angle. So if I have the opposite and the adjacent, this must be a tangent problem. So the equation I would set up to solve for my angle is that the tangent of whatever my angle is my opposite side divided by my adjacent side. Now this is just a calculator problem at this point, because to solve for an angle, I'm going to use inverse trig. So that's when you hit the second button to get that little -1. This is the inverse of tangent. And I'm just going to type in my ratio of sides. And when I plug that straight into my calculator, I get about 3.27, or like it says, round to the nearest degree. So that's just going to be 3 degrees there. So anytime I'm looking for an angle, I always want to use the inverse trig buttons rather than set up a regular ratio and cross multiply. Number 7. A wooden structure has the shape of a right triangle with a base of 12 feet and a height of 8 feet. It's supported by a wire stretched from point C to the ground at a point D, such that the support wire is perpendicular to the top of the structure, AC, as shown. So just from looking at this picture, it's a big right triangle with an altitude dropped. I'm already thinking this is either going to be a Hills problem or a SAS problem. And to determine which type of problem it is, I ask myself, do I know anything about the altitude? And I do. I know the altitude is 8 feet, so I know this can't be a Hills problem, and it has to be side 1 over my altitude equals my altitude over side 2. So it tells me how far away should point B be from point D to the nearest 10th. So I'm going to label that as x. It doesn't matter which one you label as side 1 and side 2. I'll label that as side 1 and side 2. But I'm just going to substitute them straight into that proportion. So side 1 is 12 over my altitude is 8 equals my altitude over side 2. Regardless of how you do this, you should always have the same number on that diagonal there. So when I cross multiply, I get 12x equals 64. And when I divide out the 12, I find that x is equal to 5.3333, repeating, but it says round to the nearest 10th, so I'm going to say it's about 5.3 feet. Right, so I'm just going to label that there. That's 5.3 feet as my side 2 over there. Now for part B, it says to the nearest 10th of a foot, what is the length of the support wire right there? So I'm going to label that as y because I've already used x. Now, there's a couple things we could do here. We could set up a Hills problem if we want, because we actually do know the whole hypotenuse now. I could label that as 17.3. I could label that as leg 2. And I could label that as side 2. And I could do the hypotenuse over leg 2 equals leg 2 over side 2. And it would look something like this. I'll label that as y, because that's what I'm looking for. That's one way to do it. I'm always a fan of using the Pythagorean theorem, though. Think about it. If I have a right triangle, I know one of the legs is 8. I know the other leg is 5.3, and I'm looking for the hypotenuse. I can just use a squared plus b squared equals c squared. To me, that's always going to be a little bit less work, and that formula is always easy to remember. So 8 squared plus 5.3 squared is equal to y squared. If I plug that left side into my calculator, I get 92.09 equals y squared. And remember, to undo a squared, I could just take a square root on both sides to find that y is equal to about 9.6 feet. Again, if you solve the proportion here, you'll get the exact same answer, so it's really up to you. If you want to do this as another similar triangles proportion, you can, or if you want to do it as a Pythagorean theorem, you also can. Number 8. In parallelogram ABCD, points F and G are located on side DC and AG, and BF are drawn. So the big idea here is that I know this is a parallelogram. So I gotta think about all the properties of parallelograms I know that might help me find that my two triangles AEB and FEG are similar. Now, anytime I'm doing a similar triangles proof, I always want to get to the point where I can say that two angles are congruent. So let's just start this off. If I write a statement reason proof, I have statements and reasons. The only thing I need to include in my givens is that I have a parallelogram here. So I have parallelogram ABCD. I know that's the case because they told me, so that's my given information. One thing I notice is that I have these vertical angles at E, so I could call that angle AEB and angle FEG, but just to be a little bit more clear, I'm going to label them as 1 and 2. So my first angle that I'm going to state is that angle 1 is congruent to angle 2 because vertical angles are congruent. So that's just a definition I could write down. But now I get stuck. I need another pair of angles. And I notice that if I could say that AB is parallel to DC there, I could get that pair of alternate interior at B and F. So I know this is a parallelogram, and opposite sides of a parallelogram are parallel. So I'm going to state that AB is parallel to DC, because in a parallelogram, opposite sides are parallel. Now that I've stated that they're parallel, I can make an argument that that angle at F and that angle at B are congruent alternate interior angles. But rather than try to label them, I'm just going to mark one as 3 and the other one as 4. So I know very clearly which angles I'm talking about in my picture. So angle 3 is congruent to angle 4 because parallel lines form congruent alternate interior angles. And then I'm done. I've proven the two pairs of angles are congruent in these triangles. I could have used the other pair of alternate interior angles as well. That could have saved me a step, and I didn't really need the vertical angles there, but as long as you have at least two angles, you're good to go. So I'm going to say the triangle GFE is similar to triangle ABE by angle angle. So for every similarity proof, if I'm proving triangles are similar, it's always going to be angle angle. So I don't need to prove anything about congruent side lengths here. Number 9. Given NP is parallel to QR, prove MN over MQ is equal to MP over MR. So remember, this is just, once I prove the triangles are similar, I could say that corresponding sides of similar triangles are in proportion. So I'm still going to have the goal of proving triangles are similar by angle angle, and then I'm just going to have one extra step slapped at the end of that. So the only piece of given information I have is that NP and QR are parallel, and I want to think about how that helps me. Well, for parallel lines, I'm either looking for alternate interior or corresponding, and it looks to me like at N and Q, I've got that pair of corresponding, because they're in the same place to one another, where if I translate one of them up or down, they'll land right on top of each other. So my second step is just going to be that angle 1 is congruent to angle 2, because parallel lines form congruent corresponding angles. Now I could also use the corresponding angles over here, and then I'd pretty much be done. But just for the sake of variety, I noticed that both of these triangles overlap at M. They have that angle in common. So just so I can use another reason here, I'm going to say that angle M is congruent to angle M by the reflexive property. Remember, that just means that something is congruent to itself. So I've got two angles in both these triangles, so I could say the triangle MNP is similar to triangle MQR by angle angle. And if I know triangles are similar, I know all the angles are the same and all the sides are in proportion. So I could jump straight to that proportion mn over mq is equal to mp over mr, because corresponding sides of similar triangles are in proportion, or CSS TP.